Guillaume, and I will present you some work I have done about the code of OCaml compiler. So we have two languages for OCaml. It's, as you know, a functional programming language with imperative features, and it has already a large number of libraries and programs written in it. And there is also Coq. So how many of you know about Coq? So it's mainly used as a proof language. It has also a programming part which is purely functional, so you don't have mutable states, exceptions, and you don't even have non-termination. But it has powerful features like dependent types, but a limited number of libraries for programmers. So we would like to have some bridges between the two. So to go from Coq to OCaml, it's already well known with an extraction mechanism made by Pierre Letouze, which can convert almost any Coq term or program to OCaml. So we like to do the same from OCaml to Coq with already CFML, so which can translate OCaml ML programs to deep embedding to Coq. But what I would like to do is to do a shallow embedding to have a more direct translation. And the main questions are how to import imperative programs and how to generate a simple code, which can be read by a human. So I have web time the OCaml compiler. So it takes a foo.ml program, import it to a foo.v Coq program with monads to represent the effects. So we'll explain later what are monads. And if you want, you can also compile it back to a foo2.ml program, which is not necessarily the same as the first one. Exactly, but we are ensure that they are all equivalent. So if you run these programs, you will get the same input-output traces. So the main usage will be to prove some properties about OCaml programs. So you have your large OCaml code and some critical parts, and you can import these critical parts and prove properties using the Coq language. And also, the usage will be for the Coq users. If you want to program directly in Coq, you often miss libraries. So here I hope to be able to import a lot of OCaml programs too. So we'll just show you a quick demo. Here I have some files. So if you take simple OCaml programs, like so everyone can see the generated output will be this one. So it's almost the same, except that we make explicit the polymorphic arguments.
Can you make the font just a bit bigger?
Yes. Okay. So I can take other examples. So yeah, for tuples, it's converted to tuples in Coq. If you have a intricated lets, you have also the let and the definition in Coq. So yeah, so for all this part, it's mostly syntactic conversion. But when you have imperative programs, for example, this program, the tail function, is not purely functional because it may raise an error when the list is empty. Or this function print list is not fully functional because we print and we do input outputs here. And also here we don't know if we terminate. So the output will be more complex. For example, for the tail function, here we see that we take a list of type list A, and we turn not only a list A, but also something called OCaml.failure. So we'll explain it later. And for the print list function, you have here the effect IO on the fact that this function may not terminate if you haven't proven the termination. So yeah. Now we explain exactly how imperative features are inferred and translated to Coq. So effects. So for this work, I used a simple effect system because there's a lot of literature about the system, so I didn't want to focus too much on this part. So I have no polymorph, two main restrictions, no polymorphism, and arguments of functions must be effect-free. So, for example, the list.iter function cannot be represented with the system because typically list.iter function expects this argument to do some effects to be applied. So to describe effects, we have an effect descriptor, which is a set of atomic effects. Set. Sorry. And an effect type will be the shape of an OCaml type, annotated with the descriptor of effects it can make. So every time you have a function, you may have some effects when you apply this function, which are represented by this D. And when you have an expression, you also have effects which will be raised when you actually evaluate this expression. So for example, here we have an expression which print a message and return a function which will fail. So to describe these effects, we'll say that this is a function taking a pure argument, returning a pure argument, but with the effect of failure. And to be able to compute all this expression, we'll do input outputs because we print a message here. Yeah, so how to infer effects in programs? So with this system, it's simple. We start from the inferred type of the OCaml compiler, and we do by recursion bottom-up analysis. The only corner case is for recursive definitions, and for that we just compute a fixed point. And then to represent these effects in Coq, we use monadic encoding the same way as OCaml does for effects. So monad, if you have a monad M, we say that M of A is the type of all computations returning the value of type A. And we have two primitive operators, so return to enter into the monad, and the bind to combine two computations. So here, for VFX, what we wanted to do is not to have one big monad, but one monad per FX, and to be able to compose all this monad easily. This is not possible in general, but for our problem, we took this specific shape of monad, where you have a tuple of state, and you return a new tuple of state, plus your result, or one of this error. So doing that, we can compose two monads. Compose two monads would just take the tuples of all the states, and for the errors, we just take the sum of all errors. So here are the effects we support. So we have global references, exceptions, input outputs. So they are represented as a reference to an abstract world. And the non-termination. So yes, we use the idea of fuel. So there is to bound all the computations, we have a natural number, which is the fuel, and at each step of each point, it's decreased by 1. And if you get the result, you return the result, and if the counter becomes null, before you get a result, you just raise an exception. Your function will terminate. So the implementation is OCaml. We don't support all the OCaml language, but mainly the purely functional part, mutual definitions, inductive types, records, subtypes, and the model. And we also import big parts of the pervasive and list libraries. So there are 4 compilation passes. So first we import the syntax tree already typed by the OCaml compiler. We do the inference of effects. We do the monadic transformations on the syntax tree, and then we print it into the code syntax. The main difficulties we had were to generate a simple code like a human would write, importing the OCaml programs by hand. It was hard also to support real OCaml programs because most of them use a lot of tricky features, and if you don't support all the features, your compiler will fail and you just don't get everything. It was not work to import as many libraries as possible for the functions, the primitive functions of OCaml. And the thing I didn't achieve to do was to support functors. It was too much work to support the naming system to functions. I did not have time to do it. So I did some tests on this set on map modules of the standard library of Coq. So here you have lines of OCaml, number of lines in the OCaml code, and here after importation, we can see that the increase in size is about 50%. So despite the monadic transformation, we achieved to keep a code which has almost the same size as the one in OCaml. so to conclude, it was hard to have a working compiler on real examples. For the functors, I think I should maybe we implement a lot of things to use the functions already present in the OCaml compiler to handle names inside the functors. But still, there is working implementations for handling modules and composing monads. And also, I have to study more the compilation of code with effects to go back to the OCaml.
It seems to me that if you try to prove things about a program that you have compiled, the possibility of doing this proof will depend a lot on the granularity of the compilation of effects.
Yes, yes.
So, have you actually tried compiling, proving things about small? I think the current monad that you use should be fine with local references that you can have in the state monad. But as soon as, maybe for example, as soon as you have I/O or things that use the abstract world, it's probably rather difficult to prove things about them.
You mean we like to speak the I/O to have I/O file or?
I'm thinking of if you try to explain array.get and array.set using the abstract world, because you cannot track them with the more rigid state monad, it will be very hard to put them.
Yeah. So for now, the way we will handle arrays is to have a reference to an immutable array.
Hello. I would like to know how you can use this translation to prove properties about the recursion depths of OCaml functions. In particular, I would like to know whether all my OCaml functions either are all tail recursive or have a subpolynomial stack depth, so I don't get stack overflows.
Yeah, so when you compile recursive functions to the non-termination monad, you have the fuel, which would be an explicit counter of the number of iteration. So you could do proof about the speed of execution using this explicit counter.
Okay.
What about local references?
Yeah, I don't handle local references.
Why so? Is it a problem?
Yeah, because because I thought I didn't want to focus on this subject, but I think the region inference system which will allow to do that. And, I keep that as future work. Since there's already work about this inference about local references, I wanted to focus only on the import system.
There's some differences between the way Coq inductive definitions work and OCaml polymorphic type definitions work, including having to have strictly reducing on one of the arguments. Is that something you deal with at all?
No. I assume that when you import your program, it will type check also in Coq, but there are some inductive definition in OCaml which will not type check in Coq.
You mentioned that you only support part of the list libraries. What doesn't work, especially in list library?
What doesn't work? Yes, for example, for the list.iter, since our effect system cannot handle effects on arguments, this .iter function will only be able to get pure function. So it will do nothing, because it will just return unit without doing any effect.
Thank you.